This video is brought to you by electricalexamcoach.com, offering the #1 electrical exam prep series. We have the pro version with the unlimited testing center and the free version without the unlimited testing center. We have interactive flashcards. We have full online lessons with videos and practice tests at the end. We also have unlimited practice testing on every topic that you can imagine for exam prep. This program comes with 100% full support from us here at electricalexamcoach.com. We just want to see you win. Let's get to it. Hey y'all, what's up? It's the Electrical Code Coach, and I'm super excited to offer this resource to you guys. It's 25 questions with full audio explanations. Before we get started, if you guys could do me a huge personal favor and hit that subscribe button and hit the notification bell button, that way we can spread the word and help more people. With that being said, I want to talk about the best way to use this resource. So each question, I'm going to speak it audibly and it'll list the answers below. But right after I'm done speaking it, go ahead and hit the pause button on the video and try to work through it on your own. And then you can hit the play button and see how I fully explain it and lead to the answer. I am the Electrical Code Coach. And if there's any way that I can help you in life or business, you can just email me at electricalcodecoach@gmail.com. Let's get to it. What is the total demand for the following fixed appliances? A 1500 watt kitchen mixer, a 1500 watt dishwasher, an 1100 watt garbage disposal, and a 3500 watt water heater, and a 1200 watt central vac system using the standard method. First, we're going to total all of our fixed appliances, and that's going to give us a total of 8800. Now we remember the 75% rule for 4 or more appliances when we're using the standard method. And we apply that demand factor. We take 8,800 multiplied by 0.75. That's going to give us 6,600. And we select C. All right, so let's do a little more complicated one. What is the total cubic inch volume you would have for a box that contained 6 hot conductors, 6 neutral conductors, and 6 equipment grounding conductors, all 12 gauge in the 2020? So the first part's real easy. We take our 6 hots, our 6 neutrals. We're going to take each one and multiply it by 2.25. That's going to give us 27 cubic inches, okay, that we've taken up so far with these conductors. Now we have to calculate it for our equipment ground. So for the first and up to 4, it's going to count as 1 based off the largest conductor in the box. Our largest conductor is a 12, so it's going to count as a 1 number 12. Okay, then we have to do the 1/4 inch increase for each conductor past 4. So the easiest way to do it is take our total equipment grounding conductors. 6 minus 4 is going to equal 2. So we have 2 that we need to increase. We take 2, multiply it by 0.25, and that's going to give us 0.50. Now we have to take that and add that back to our original 1. 1 plus 0.50 equals 1.50. Now we have to take that and figure out what it is in cubes. So we take our 1.5 conductors, multiply it by 2.25. That's going to give us and I round it up to 0.8. Okay, so it's 3.38 instead of having some long number. Now we need to take and add that back to our original cubes. That's going to give us 3.38. You add those two together, and that is going to equal 30.38. And we would select C. So you guys can see how this is super complicated, and hopefully the code makers will get together with public input. Typically, guys, how this happens, so you probably don't have to worry about it, is typically what happens is it comes out the first time in the code. Sometimes it's a disaster. Then they regroup. You know, the code maker panels are awesome, and this is just something, you know, they're trying to deal with a huge problem here. So this is not anybody's fault. They're trying to deal with, well, what if we've got 9 equipment grounding conductors in the box? They need to account for something, and I get it, but this may or may not have been the way to handle it. So I'm not going to say it's not the way to handle it, and then we have to look at this question as an example here. It would have counted as 1 in the 2017 and previous. We've added 0.5. Is it going to make a difference in our box fill, like our actual box fill? Now, if you get into 10 equipment grounding conductors, it might. I don't know. But, I mean, is it going to push you into a larger box? I'm just not sure. So it's something that they're going to work out. You know, I love the code makers, code making panel. I think it's an excellent process. I'm not putting down anybody. Just this one here, as far as testing purposes, I feel like it just got out in the weeds. And hopefully they'll bring it back, and I have confidence that they will. I am the Electrical Code Coach. Let's go ahead and get to it. How many number 8 conductors can you fit inside of a 4 by 2 1/8 by 1 1/2 device box? So the first thing we're going to do is we're going to find our box. It told us two of the knowns, the box and the size conductor. So we're going to go down and we're going to find our box. Now we're down into the device boxes, and there are a bunch of them. So we need to get into the 4 section because it goes 3, 3, 3, and then jumps up to 4. So we're looking for device boxes, and we are looking for a 4 by 2 1/8 by 1 1/2. So that's the first one there when we get to the device boxes that are in the 4-inch section. Now we need to come over and we need to find a number 8 conductor. So we're using a piece of paper or some type of straight edge. We come over and we find that it is 3 number 8s. So we've looked at our table and we find out that it's 3 number 8s. We found our box, we slid over to our respective conductor, and right there we teed off and we found out that it is 3. Great job. What size overload protection would you select for a 7.5 horsepower, 208 volt, 3-phase motor terminating to 75 degrees C terminals with a nameplate current rating of 23 amps marked with a temperature rise of 32 degrees C? So we're going to work through the motions again. We do have a temperature rise. For this motor, we're going to use 125%. Now we do our math. We take 23 multiplied by 1.25, and that's going to give us 28.75. Now, they do not make a 28.75 amp breaker, but remember, we have to use for motor overload protection only, we have to use the next size down. It's going to be 240.6A, and we're going to select a 25 amp overcurrent device. Great work. What is the total cubic inch volume you would calculate for a box that contains 3 internal clamps and 4 12-gauge conductors? Now we're going to work right back through our rules, and if you ever forget any of these numbers, you can head to 314.16 using your box sizing tab, and you can read through there. And you've got plenty of time in the testing center. It's just a couple black bold headings that you have to read that will give you the count that you need. All right, so let's go ahead and work through this one. We're going to go first to our table, find our individual volume. We're going to find that each one is 2.25, and all internal clamps in the box only count as a total of 1 based off the largest conductor that's inside the box. So we're going to take 4, which is our base number, 12-gauge conductors, and then we're going to add 1 because we have 3 internal clamps, but they only count as 1 altogether. We total those two together, it's going to equal 5, and we're going to take 5 multiplied by 2.25. That's going to give us 11.25, and we are going to select C. What is the smallest round octagonal box you could use to fit 3 10-gauge conductors and 3 12-gauge conductors? So we're going to head to 310.16b. And then what we're going to do is find out what the cubic inch volume is for a 10-gauge conductor. In this case, we find out that it's 2.50, so we're going to multiply that by our 3 conductors. That's going to give us 7.5. Then what we're going to do is we're going to find out what the cubic inch volume is for a 12-gauge conductor. And in this case, it's 2.25. So we take 3 multiplied by 2.25, and that's going to give us 6.75. Now, when we take and add those together, it's going to give us 14.25. So that's step 1 done. We needed to find our total cubic inch volume. Now what we're going to do is we're going to find the smallest box. So we're going to head to table 314.16a. And what we're going to do is we're going to look in that little skinny column right in the center where it's the minimum volume column. So we need to make sure that we're in our right box selection, which the round octagonal boxes are the first 3. So I come over here to the inches cubed column. I slide down and find one that's big enough to fit 14.25 in it. And it looks like the second one. So when I go back over and I find my box trade size, I find that it is 4 by 1 1/2. Great job. What is the total demand for 57 ranges with a nameplate rating of 8,900 watts? Our range falls in between 8 3/4 and 12, so we're going to be using column C. On the left-hand side, we slide down and find our number of ranges. Then we slide over and we find that column C states that we must use a 25 kW base and then add 3/4 more kW per range. So let's find out what our increase is going to be. We take 57 ranges multiplied by 0.75. That is going to give us an increase of 42.75. We add that back to our base. That's going to give us 67.75. We round up and we select B. What is the total HVAC demand for a dwelling unit with the following loads on a 120/208 system? air conditioning at 23.2 amp compressor with a 3.8 amp blower motor for the system, and a heating of 24 kW heat strip. We're going to choose the larger of the two. First, we're going to do the AC. We're going to take it and multiply that out, and that's going to give us 4,825.6. Then we're going to take and multiply that by 1.25, and that's going to give us 6,032. Now we're going to add the blower motor. That's going to add another 790. We're going to take and add those two together, and that's going to give us a total AC demand of 6,822. Now let's do the heat. So we take our 24 kW, and we're going to add the blower motor to it. That's going to give us 24,790. Our AC, we line up our heat. We're going to omit the smaller, and we're going to select B. Let's get to it. What size main overcurrent protection would you select with a total calculated load of 189 amps on a 120/208 three-phase system? In this case, all the hard work has been done for us. It is three-phase, so you would think you might have to multiply by 1.732, but in this case, we already have the amperage. So if the amperage is already known, there's no additional multiplication needed. We're going to take our 189 amp load. We're going to head to 240.6A. We're going to select the next standard size, and we're going to select a 200. Let's get to it. Let's take a look at the same scenario, but with single phase. What size main overcurrent protection would you select for a total calculated load of 142,250 VA on a 6-unit apartment complex on a 120/240 single phase system? So we're going to divide the total VA by the system voltage. So we take and bear that math out, and it's going to give us 592.70. We're going to round up to 593. Then we're going to head to table 240.6A. We're going to choose the next standard size, and in this case, that's going to be a 600. So you can see the significant difference when we go from three-phase to single phase in sizing our services, our wire, and everything else that comes along with it. Let's get to it. What size copper THHN service conductors would you select for a commercial building with a total calculated load of 49,250 VA on a 120/208 volt three-phase system terminating to 75 degrees C terminals? We're going to divide the total VA by the system voltage. With three-phase, we must do some pre-work. We take 208 multiplied by 1.732. That's going to give us approximately 360. We take our total VAs and divide it by that number. That's going to give us 136.7 amps. Now we're going to head to our primary ampacity table. We're going to head to the 75 degrees C column for copper, and we're going to select A. What is the allowable ampacity of a 4-aught THHW copper conductor that's installed in a pipe with 12 current carrying conductors? We're going to head to the 90 degrees C column first. And we're going to find that 4-aught is good in the 90 degrees C column for 260 amps. Then we're going to head to our respective tables. And we're going to find the adjustment factor for 12 current carrying conductors is 50%. So we take our original ampacity, we multiply it by 0.50, and that's going to give us a new allowable ampacity of 130 amps. And we select D. All right, we're going to do a general lighting demand calculation before demand factors. So we're just going to be dealing with the square foot VAs and the small appliance VAs. One thing I do want to note when you're doing the optional method, all of this original part is exactly the same as doing the standard method. So we just change gears. It's when we apply our demand factors and do our appliances that the game really changes. So let's go ahead and just refresh. What is the total general lighting demand before demand factors for a dwelling unit that has 4,300 square foot of main living space, a 400 square foot sunroom, and an 1,100 square foot detached garage? So we're going to total the total square foot in our calculation. We will count the 4,300 square foot of main living space. We're going to count the 400 square foot of sunroom, and we're going to omit the 1,100 square foot of the garage. It's the same principle and the same rules as if we were doing the standard method. So we're just going to take that and we're going to multiply it by 3 VAs per square foot. We're going to bear that math out, and that's going to give us the 4,700 square foot. And then we are going to go ahead and multiply that by 3, and that's going to give us 14,100. Now what we're going to do is we're going to have to add in the 4,500 VAs for the small appliance. So all of the same process, all of the same rules, all of the same steps up until this point, and we just add those two together, and that gives us a total general lighting demand of 18,600 VAs, and in this case, we're going to select B. Now let's do another one, and we're going to do the demand factors. So it's going to be the same process as doing the standard method right up until we input what the demand factors are. Same process, different inputs. Let's go ahead and jump into it. What is the total general lighting demand after demand factors for a dwelling unit that has 3,300 square foot of main living space with a 400 square foot front porch and an 1,100 square foot attached garage? So first we're going to determine the total square foot that's included in our calculation. We will count the main living space, we're going to omit the front porch, and we're going to omit the 1,100 square foot garage. So we do it at 3 VAs per square foot. So we take that 3,300 multiplied by 3, that's going to give us 9,900. Then we're going to take and add in our 2 small appliance and 1 laundry circuits. So we take that and add that all in, and that's going to give us 14,400. Now this is where things change a little bit. We're going to head to 220.80, and their demand factors are a little bit different percentages. Same process, different percentages. So we take the first 10,000 at 100%, and we're going to take the remainder at 40%. That's it. So we take our 14,400, we minus 10,000 right off the top, and that's going to give us 4,400 left to apply the demand factor to. So we take that, we multiply it by the 40%, and that's going to give us 1,760. Now we have to take and add back the original 10,000, and that's going to give us 11,760. And we're going to select A. I love the optional method. It's a lot easier to work and deal with. Now, next week, we're going to pick up and we're going to jump into dealing with the appliances. And then we're going to work for that week, work together, and then we're going to put it back together into one piece, into one whole home. And, we're going to do a commercial one as well for the optional method. Let's go ahead and get to it. What is the allowable ampacity of a 4-aught XHHW aluminum conductor that's installed in an area with an ambient temperature of 55 degrees C? We're going to start in the 90 degrees C column. We're going to find that 4-aught in the 90 degrees C column for aluminum is good for 205 amps. Now we're going to head to our respective tables. We find the temperature correction factor for 55 degrees C, being sure to start on the left-hand side of the table because our ambient temperature is in Celsius. Now we're going to head and tee off with the 90 degrees C column for our correction factor. We find that it's 0.76. Now we take the original ampacity, multiply it by 0.76, and that's going to give us a new allowable ampacity of 155.8. And we select B. Great job. Let's do one more easy one as a refresher before we get into the more complex calculations. What is the total demand for 2 dryers with a nameplate rating of 5,100 watts each using the standard method? Remember, when we're using the standard method, we calculate the dryers at a minimum of 5,000 VA or the nameplate rating, whichever is greater. We take 2 multiplied by 5,100, and that's going to give us 10,200. Then we head over to table 220.54 and find out what our demand factor is for 2 dryers. When we get to that table, we find out that there is no demand factor. You calculate it at 100% up to 4 dryers. So we just take straight math, 2 multiplied by 5,100. That's going to give us 10,200. And the total demand for this one is A, 10,200. Great job. What size copper conductors would you select for a 10 horsepower, 230 volt single phase motor that has an FLA nameplate rating of 47.5 amps, terminating to 75 degrees C terminals? So we're going to come down here. We're going to go through all of our initial steps, being sure that we head to table 430.248 for single phase. When we get there, we're going to come down, we're going to do our process, and we're going to find out that this motor's FLC is 50 amps. Now, I wanted you to notice that I did the same size motor as far as horsepower, and we doubled the voltage and took it to 430. And when you do that math, it cuts our amp draw in half. So I want you to think about that as we do this problem. So this motor's FLC is 50 amps because we doubled our voltage. Now we're going to take that 50 and multiply it by 1.25. That's going to give us 62.5 amps. Now we're going to head to our primary ampacity table in the 75 degree C column, and we're going to come down and we're going to size our wire to a number 6 gauge. So I want you to notice when we doubled the voltage, it cut our amperage in half, which allowed us to size our wire in half. That is the advantage of two wires containing, two hot phase conductors, is it's going to cut your amp draw in half if all things are equal, okay? In the same way that three-phase ultimately does the same things, all things being equal. So it's just one of those things that how you can reduce the load, which ultimately allows you to reduce the wire, which ultimately allows you to reduce the pipe and all the other things, considered. So I hope you guys enjoyed that one. What size short circuit ground fault protection would you select for a 5 horsepower, 208 volt AC, 3-phase motor terminating to 60° C terminals with a nameplate FLA rating of 26 amps using an inverse time breaker? We never size normal short circuit ground fault protection from the nameplate or FLA rating. It's just like normal circuit conductors. You're going to size it from the motor FLC. If the FLC is printed on the nameplate, we can use that. First thing we're going to do is go figure out what our FLC is. We know how to do this. Pause the video now. See if you can find out the motor FLC. So we use our FLC motor tab. That takes us to table 430.248. We're doing 3-phase, so we need to flip over to 430.250. We're going to look down and find a 5 horsepower motor. Then we're going to slide over to our respective voltage. And in this case, it's going to be a 16.7 amp motor. What size short circuit ground fault protection would you select for a 5 horsepower, 230 volt AC single phase motor terminating to 60° C terminals with a nameplate FLA rating of 26.9 amps using an inverse time breaker? We're going to use our FLC and not the nameplate FLA rating. We're going to head to table 430.248 because it's single phase. We're going to find that our FLC is 28 amps. Now we're going to head to table 430.52 and tee off and find out that ours is 250%. Now we're going to take our FLC, multiply it by 2.50. That's going to give us 70 amps. Now we're going to head to table 240.6a and choose the next standard size. In this case, it falls on a standard size, and it happens to be B. Let's get to it. What size short circuit ground fault protection would you select for a 5 horsepower, 120 volt AC single phase motor terminating to 60° C terminals with a nameplate FLA rating of 46.9 amps using a non-time delay fuse? So we're going to use our FLC and not the nameplate FLA rating. We're going to head to table 430.248 because it's single phase. We're going to find that we have an FLC of 56 amps. Now we're going to head to table 430.52 and we're going to find our motor and device and find out that it's a 300% multiplier. We're going to take 56 multiplied by 3.0. That's going to give us 168 amps. Now we're going to head to table 240.6a and we're going to choose the next size up. And in this case, it's going to be 175. Great job. What is the total cubic inch volume you would calculate for a light box that contains 3 12-gauge, 3 14-gauge, and 2 field-applied internal box clamps present inside the box? So we're going to look at table 314.16b. We're going to pull our individual volume for our 12-gauge. All internal clamps are going to be 1 based off the largest conductor in the box. In this case, the 12 is the larger gauge conductor. So what we're going to do is we're going to take our 3 base 12-gauge conductors and we're going to add them to the 1 internal clamp. And we're going to do it on the 12-gauge size because it's the larger one in the box. That's going to give us a total of 4. We're going to take 4 multiplied by 2.25. That's going to equal 9. And we're going to do the same thing for 14. We work through the math. It gives us a total of 6. We take our 9 plus 6, and that's going to equal 15. And we select D. Great job. How many number 8 conductors can you fit inside of a 4 by 2 1/8 by 1 1/2 device box? So the first thing we're going to do is we're going to find our box. It told us 2 of the knowns, the box and the size conductor. So we're going to go down and we're going to find our box. Now we're down into the device boxes, and there are a bunch of them. So we need to get into the 4 section, because it goes 3, 3, 3, and then jumps up to 4. So we're looking for device boxes, and we are looking for a 4 by 2 1/8 by 1 1/2. So that's the first one there when we get to the device boxes that are in the 4-inch section. Now we need to come over and we need to find a number 8 conductor. So we're using a piece of paper or some type of straight edge. We come over and we find that it is 3 number 8s. So we've looked at our table and we find out that it's 3 number 8s. We found our box, we slid over to our respective conductor, and right there we teed off and we found out that it is 3. Great job. Let's look at it from another angle. What is the maximum cubic inch volume of a 3 3/4 by 2 by 2.5 masonry box? So this is asking us, what is the total volume available? And we learned about this here a minute ago. Now we're going to tie it in because this is super important when we get ready to start doing the other box fill type calculations. So let's go ahead and look at the table. First thing that we're going to do is we're going to find our box. So it told us the type of box and it told us the dimensions. So when we go down here in our types of boxes, we find that there's only 2 masonry boxes that are listed. So let's start at the first one, 3 3/4 by 2 by 2.5. That's us. So we're going to lay our piece of paper or our straight edge down, and where we're going to find the cubic inch total is in that middle skinny column. You see the minimum volume column? Remember how we learned about the inches cubed? So what we're going to do is we're going to go and we're going to slide over, making sure that we select from the inches cubed section and not the centimeters cubed, and we're going to find out that it is 14. So the maximum volume of this box is going to be C. It's 14 cubic inches. That's the max volume. And this is really going to come into play next week when we start working through individual conductor sizing. This video is brought to you by electricalexamcoach.com, offering the #1 electrical exam prep series. We have the pro version with the unlimited testing center and the free version without the unlimited testing center. We have interactive flashcards. We have full online lessons with videos and practice tests at the end. We also have unlimited practice testing on every topic that you can imagine for exam prep. This program comes with 100% full support from us here at electricalexamcoach.com. We just want to see you win. Let's get to it.